But otherwise, thanks again, Adam, and I'll get started. So this evening, I'll be presenting my research, which I've been looking at over the past year. As the title quite literally suggests, it's focusing on predicting marimba stickings using neural networks. The presentation this evening takes place in 5 parts. Firstly, I'd like to outline the sticking problem that marimbists face. I'll then talk about machine learning as a methodology that we can use to approach complex problems. And I'm particularly interested in demystifying machine learning so it's not surrounded with the vagaries and complexities that might often be assumed with it. I'll move on to talking about my own methodology on how I'm implementing these systems for the sticking problem. We'll talk about results and conclusions and the future directions of the research following that. So beginning with the sticking problem. Now, as all musicians in the room will attest, technical problems can arise when we try to play music. Perhaps our fingers get tangled when we play clunkily, perhaps we bow differently to our neighbours, or we use the wrong fingering, maybe we breathe in the wrong place and we break a phrase. Now, our practice and our experience, and sometimes sheer trial and error, influence the way we overcome these issues, and we learn how to solve problems in the new music that we play through all the experience that we've had of the music we've played in the past. Of course, the music we've played in the past is based on the music of its past, and so on and so forth. Hence, we draw on and contribute to a lineage of our instrument, this collective technical and musical tradition. However, what if the instrument has a limited history? Now, the marimba came to mainstream Western popularity around the 1960s, and with only around a 70-year history in the Western art world, it's really a baby compared to the other instruments, and yet it's still such a core component of every Western percussionist's training. But just like everybody else, marimba players face the same technical challenges, one of the biggest being that of sticking, that is, which stick plays which note. Now, marimba players often play with 4 sticks, and as you can see, maybe corresponding to what you see on screen, we've got stick 1, 2, 3, and 4. So it's really a question of how do we play all the notes that we have to play so we don't tie ourselves in knots, and so we can play it in a musical manner. There's only a little bit of advice in the existing literature that helps us guide our sticking choices. Nancy Zeltzman advises the principle of aiming for minimal overall movement and introduces the concept of using a free hand. Norton and others argue that the easiest or most natural sticking is not always the one that will result in the best musical interpretation. And as for what can guide us towards a relation between sticking and fluent musical performance, we really have minimal methodology. This, combined with our limited lineage, our limited repertoire, and our limited collective experience to draw from, means that our ability to solve these kind of problems are skewed towards a trial and error approach. I'd like to just demonstrate with you what I mean. And at this moment, if you can swap your screen over, you might find it useful to do so. So what you'll be seeing on the PowerPoint presentation is a set of 8 notes from Joseph Schwantner's piece, Velocities. It's just a really short excerpt, and it's naturally stuck using a 1, 2, 3, 4 sticking that looks like this. So that's all well and good, and it seems easy enough that we should be going 1, 2, 3, and 4. But observe what happens to the 4 as we explore a larger context of the piece. With this new section, we've had to reach across with this mallet so that we can manage the legato phrasing on the way down. So what this is showing us is that the way we stick doesn't just depend on the notes, but it depends on their placement and their context, where they're situated in the music. Of course, further confiscating this idea, if we look yet one step further into the next bar, we see the same figure. However, again in a different context, it makes us revert back to our original sticking of using the 4. And now we have to reach over with our hand to play this top sequence. Again, for the legato feeling. All right, let's switch back. So these kind of examples here, these changes in sticking that depend on the context of the notes in the music, demonstrate the sticking problem. These stickings that I'm playing are stickings that I've decided to choose, and really they've originated from very much a trial and error point of view. And this process is tedious at best, and if one chooses poor stickings early in education and follows the path that this leads, this can be detrimental to development and risking injury at worst. So I'm proposing a computer-assisted guidance towards sticking, drawing upon the artificial intelligence approach of machine learning. This would involve developing a program that learns how to choose stickings based on a large set of repertoire, as stuck by world-class performers. For both students and professionals, such guidance might provide a stronger point of departure for solving technical issues, making music learning faster and more efficient. And it may also help supply students with a readily accessible kind of digital teacher, offering well-constructed sticking suggestions that can contribute to developing technically and contribute to building a stronger long-term performance lineage. So let's talk about machine learning then. You may have heard of this term in recent years as the technology has become increasingly accessible. Now, machine learning can be summarized as the programming of computers to learn from data. Now, traditional algorithmic programming approaches create sets of rules to solve problems, but machine learning reverse engineers this process. The problems to be solved are encoded alongside many example solutions, and we let the computer figure out how to get from problem to solution. In this sense, the computer figures out its own set of rules, and we say it learns. I'd like to give a high-level overview of machine learning to try to demystify what it really means when we say that a machine learns. Consider this circle, representing a simple maths function called a neuron. It stores some simple numbers that help it make calculations. We'll call them weights 1 and weight 2, but they're random numbers for now, and we'll worry about them later. Now let's take a trivial problem. For example, suppose we're trying to make a decision, should I be practicing? Let's ignore the obvious answer of yes and give 2 example inputs. For example, how many hours have I already done today? And maybe how many days until my history essay is due? Now in this example, if I've not practiced at all yet, and my essay is due next month, then perhaps I should be practicing. To the computer, this is equivalent to saying that 0 lots of weight 1 and 31 lots of weight 2 should be equal to 1. Now the weights give us an idea of how important each input is. So maybe how many hours I've done is really important to this calculation, and maybe how many days until my essay is due is not so important. We don't know what these weights are, but it's not our job to figure out. Now, conversely, if I've already been practicing for 18 hours today and my essay is due tomorrow, then maybe I shouldn't be practicing. I should probably be reconsidering my life choices. But again, the computer wants to solve 18 lots of weight 1 and 1 lot of weight 2. This time might have to equal 0. But of course, these weights were randomized initially, and the computer has no idea the context of these questions. It can't magically solve our problems for us. It's going to give us complete garbage. Rather than trying to figure out which weights give us a good answer, instead we can get the neurons to do it by programming just a few processes. We'll tell it, hey, if you see an 18 and a 1, give me the answer 0. If you see a 0 and a 31, show me the answer 1, and so on. We feed it all of these examples, called training examples, or training data. And each time, the neuron calculates the output as before based on the weights, called feeding forward. Now to learn, we subtract its guess from the real answer to calculate how wrong it is. This is an error which we'll call loss. Now obviously the smaller our error, or the smaller our loss, the better our prediction. So we reduce our loss by adjusting our weights up or down a little bit in a process called gradient descent and backpropagation. Now I'm going to gloss over the maths for now, But hopefully you can see that if we change our weights just a little bit, there's a possibility that our output might be slightly closer to the correct output. And if so, we'd keep that change. We repeat this process many, many times, and the machine will slowly learn with fewer and smaller errors. Then, of course, in theory, we can ask it something that we've never asked before, and maybe something that we don't know the answer to. And now it can tell us what it thinks, based on the patterns that it's seen. So, in reality, this neuron example that I've given is probably far too simple to even answer the practice question. A single neuron can only do so much computation, but we can chain these simple neurons together into big networks that are capable of solving much more. But the process is identical. We feed it inputs, we calculate the loss, and we adjust the parameters, like the weights, and we repeat this process. By the end of the training process, we have this big neural network that has adjusted itself to match a whole range of example problems, this training data, and can help us find solutions to new problems. This is the premise behind machine learning. So, why machine learning, of all approaches? Firstly, the sticking problem largely depends on what is considered musical. This is a difficult metric to begin to quantify to begin with, and many conventional approaches have been tried with little success in trying to capture this nebulous term of musicality. Secondly, machine learning provides insight into what features in our music are important and relevant to sticking choices. Now, in this study, I'm only looking at two musical features, pitches and durations. However, this approach allows us to, in future, incorporate other musical features, things like tempo or dynamic, articulation, and we can incorporate these in and out of models to see the degree to which they change our results, and from here we can see the degree to which we might be wanting to consider them as we make our sticking choices. Finally, this technology is transferable. Now, percussionists, we perform behind marimbas, but we perform behind many other instruments as well, and in many different setups and contexts. And this technology or this approach is quite easily transferable to other instruments, and possibly even other non-percussion instruments in general, pianists and string players in particular looking at you. I find it interesting that composers have been using machine learning approaches for decades in generative algorithms for music. I'm sure you've all heard of the idea of computers generating Bach chorales. So I think it's interesting to see where the value lies for a performer or in a performance context. So onto the methodology. All machine learning begins with data. And for my study, I'm going to be comprising, my training data comprises the set of exercises written by seminal marimbist Leigh from his book, Method of Movement for Marimba. The book contains 590 exercises, and when we include the variation on some of these exercises, it becomes around 842, which I've transcribed into a machine-readable format, which you can see at the bottom of the screen. Now, each transcribed exercise is in C major, and Stevens writes that one should transpose them to each key and play in all parts of the marimba. After iteration, this amounts to over 32,000 exercises for the model to learn from. Actually, this is still a pretty small data set, but despite this, it forms an important contribution to any future work on machine learning in keyboard percussion. Now, these machine-readable spreadsheets are converted into 62-dimensional arrays containing note information and the corresponding 4-dimensional arrays containing sticking information. So for each note, and there's a total of 545,000 notes or so. In English, you remember the neuron I had earlier with two inputs, how many hours have I practiced today and how many days into my essay is due? That had two inputs, so this network has 62 inputs. 61 corresponding to each note on the marimba, and a 60-second input for the duration of that note. You can see these represented here. With this, I've encoded the solutions as shown in a 4-dimensional array, and in this example, this would represent the sticking 3, 4 for these two circled notes in the array. I think that might be an E and a C or something like that. So the array would be saying, play these two notes with stickings 3 and 4. Now, I want to note that each note on the marimba is encoded separately in each of these 0 values that you can see here with the two 1s, for an important reason. we realize that the implications of playing a C on a marimba, my headphone cable is not going to stretch this far, but the implications of playing a C are very different to the physical implications of playing a C sharp. This can, of course, lead to many sticking issues. However, if these were represented in MIDI values, for example 60 and 61 for middle C and C sharp 4, the values would be so close that it would be difficult to differentiate these physical differences. And of course, the irregularity of naturals and sharps on the keyboard would exacerbate the problem. So this is called one-hot encoding, and it's the encoding method which I've chosen to alleviate this issue. From this dataset, we can develop a model to learn from the data. My baseline model is a 10-layered LSTM network connected to 4 output neurons, 1 for each stick. It uses the categorical cross-entropy loss with the atom optimizer and using a softmax activation. You don't need to worry about every word there, but these options that we have are called hyperparameters of the model. So I adjust the model not by adjusting the weights, in the internal parameters of the model, but by adjusting the hyperparameters of the model, which govern the global structure of the model. So far, I've been experimenting with 2 hyperparameters. Firstly, the activation function, changing it from a softmax to a sigmoid function, and this allows for the inclusion of things like double stops and chords, as the softmax function is mainly used to classify inputs into a single category, for example, just a 1, 2, 3, or 4. So doing this allows an expansion of this scope of the project. Secondly, I recognize sometimes that a sticking choice is not only determined by the notes that come before, but also the notes that follow. And to try and give this look to the past and to the future, I've implemented what's called a bidirectional layer, which essentially means that the model may be able to read the music backwards as well as forwards to determine stickings. This generates a total of 3 more models, which I can then compare the baseline with. Now, in practice, there are many, many hyperparameters that can be changed to optimize network performance. These include things like changing the network size, the learning rate, the model of the network itself to GRUs. But for the scope of this study, I'm going to limit the variations to just the 2 discussed. Now we can build and fit our models to the data, and we can use these models to predict stickings. That's an example shown below, actually taken from the models that have been generated. However, in truth, there's a bit more to it. The model is faced with a host of limitations. Firstly, we have a lack of data. Music data needs to be computer readable, of course, for this methodology, but unlike the plethora of digital piano scores or guitar tabs that are available online, there's no real accessible digital repository of marimba scores. And this is why a large part of my research has been involved in creating the Leigh-Stevens dataset. Even then, as I mentioned, it's quite a small set, and we'll talk about the implications of this later in the presentation. Secondly, the type of data. Notably, the only data going into this model are Leigh-Stevens style permutation exercises. Now, there are quite a few reasons why I chose to transcribe Leigh-Stevens. In summary, Leigh-Stevens' book has around what we're looking for in terms of quantity and quality for this type of methodology. But at the end of the day, they only are exercises, not reflecting the actual music that marimbas play. So the model then is being tailored to learn how to stick Leigh-Stevens style exercises rather than actually predicting music itself. So predicting musical excerpts might be a bit of a roll of the dice. Finally, the idea of data bias is present in this model, as it is present in many machine learning contexts, and it regards the balance of our training data. For example, if my dataset has far more monophonic exercises as compared to chordal exercises, that is, if it's more common for me to play 1 note at a time in the exercises as opposed to chords, then my model will tend towards outputting more monophonic solutions, just because they're more often right. Even if I put in a chord input, it might give me a monophonic solution. And again, this is a real output that's been generated by the models. Luckily though, in my dataset of exercises, it's quite balanced between a monophonic and chordal split. However, there are finer elements of bias that are imbalanced. For example, 3-note chords don't feature in Leigh-Stevens exercises at all, so it's unlikely that the model will ever predict a 3-note output, even if 3 notes are given. Now, I've programmed the prediction model to force pick the number of stickings equal to the number of notes in the input. For a predictive model, this makes more sense for a prediction, and it reflects meaningfully the inputs of the double stops. But I just want you to be aware that it does also hide some of the biases that are going on under the surface. So with that all said, let's look at the results. Evaluating these models through k-fold cross-validation with k equals 5, the models perform as shown. Now these models were trained and validated on 90% of the Leigh-Stevens set, with 10% set aside for later testing. Our highest performing model, the softmax bidirectional, certainly shows promise. Additionally, given that many exercises in Leigh-Stevens have many different sticking options, and that any particular prediction of the model is only ever marked against one of these options at a time, we can expect to see false negatives in validation. And as such, these scores that are presented here might be on the low side. We do have to temper our excitement for a couple of reasons, though. Firstly, if we look at the learning curves of the models, we see a trend that they tend to perform better in training than in validation. You can see here that the blue line, which represents the training, has a lower error, or has a lower loss than the validation line. And this indicates that our model is performing well on the training data, not because it's starting to understand the stickings of the patterns of sticking, more because it's starting to memorize the solutions to every exercise and use that memorization technique in the same way that somebody might try to memorize all the solutions to a math exam before going into the exam and getting steamrolled for real. This is further evidence of this issue was revealed in evaluating the models against a test set, that 10% which we set aside earlier, after cross-validation. We got a consistently lower performance of between 2 and 8%. This problem is called overfitting, and it's primarily caused by running too many iterations with too little data and on too complex a model. This is actually a design limitation we've already addressed, and it's one of the biggest hurdles, that of our small dataset. In fact, by iterating the training dataset to go from our 842 exercises to our 32,000, we possibly even exacerbate the problem. So this really draws attention to the need for increased accessible digital Marimba scores. Now, numerical results are all well and good, but let's see how this fares in a subjective sense. So this one, in real life, I isolated a set of 50 exercises from that test set and had the models predict the stickings for each of these examples. So 200 total sticking annotated exercises were shuffled, and I subjected myself to a blind test, evaluating each of these examples and the stickings from each of these examples from 1 to 5, and rescaling to a percentage from 0 to 100. This evaluation, of course, is based on my own experience as a player. There's nothing objective here, and it doesn't necessarily capture any good or bad qualities or insights that are brought about by the machine learning models. However, that said, averaging the results for each model, we get the following results. Notably, they're all almost the same. There is an outlier here, which at first I thought was because of my own inconsistency in subjective evaluation. However, I have actually seen this crop up in a few prior naive tests, so I think further testing will be required to determine the significance of this outlier. But the trend is that we're seeing overfitting, and we're seeing that there's a flat performance in qualitative evaluation. And this really allows us to reinterpret our quantitative scores that we saw earlier differently. I'll note so far that only 2 hyperparameters have been tested. Of course, the activation function and the bidirectional layer. And the qualitative testing was over a relatively small sample size of 50. Furthermore, 50 exercises from Leigh-Stevens itself. However, despite this, the biggest variation in performance was not between the models, but between the different exercises that the models were given. The models just seem collectively better at predicting some types of music than others, which suggests dataset bias. And it's actually affirming to see this result, because it's something that we did predict in our design limitations. So this suggests that rather than trying to optimize our models further and looking for further hyperparameters, focus should be drawn for now on developing the quantity and quality of our Marimba datasets. So, how does this all reflect my initial goals? Initially, I'd set out to assist Marimba players by providing a means of predicting stickings. Now, well, I have a set of models which do suggest stickings, even if performance can be improved. In the past few minutes, I've been quite critical about the limitations and the issues with the models, and of course the junk like this that it can put out. However, I have also during this process encountered stickings from the models that have opened my eyes to alternative, technically facile and musically sensible stickings that I would never have thought of. Here is the passage that I demonstrated earlier from Schwantner, but with the middle stuck by the machine in a very different manner. I'd like to draw it as a comparison to what we saw earlier. Here, you may choose to switch over your video again, but what we saw earlier in my example of Schwantner was the idea of using double lateral strokes for a very legato feel. So you can see that my hands are just rolling off like that. However, the model was suggesting the idea of doing an alternating sticking. So the effect of this would be a legato bottom emerging into a more articulate and clear top using a different sticking before submerging back into a legato descent. It would sound something like this. Sorry, one more time. So, where are we? Perfect. Thanks, Adam. So, just to conclude, I'd like to finish with the idea that even though these machine learning models are still a work in progress and that there's things to be developed on, they've already taught me something. And with these models already assisting marimba players, or just one marimba player for now, but with a clear path towards further development, I think this is promising research that has already contributed and hopefully will continue to contribute towards the development of marimba sticking technique and a stronger marimba lineage into the future. That's all I've got today. Thank you.